Good morning, everyone. Uh, it's my first time to come to the QT conference, so I'm still nervous now. And first I want to thank a lot of people, especially Professor Bai. He fixed my USB file yesterday, so I can go through very smoothly. And
Bai is me. My name is surname in Chinese.
And I want to thank you, Professor Louis Chen and Professor Stan's encouragement and Professor Harvey. They gave me a lot of encouragement so I can stand here very strongly. Thank you very much. Today my topic is nonlinear functional of space noise. And I want to also thanks visiting Nagoya University 2 years, give me a good research environment. And I also want to thank Professor YJ Lee and Professor Shi Xinhong, who then give me a lot of encouragement to do the research. And also I want to thank the conference give me the chance to have deliver my speech. This is some summary of my paper, but if the time is permitted, we will go back to see it. Yes. And my research is focused on the person process P and the P because a lot of people do it the P dot T is focused on PP. But I'm focused on space lambda intensity. So I do the P prime lambda to investigate the noise. So we call it a new noise or a space noise. So my speak will focus on the P prime lambda. And first we will give some introduction. Actually my research is promoted by the Levy's paper, Paul Levy's paper. And in our common known three noise is white noise and proton noise. But they are focused on the time parameter. And the third one is what I research is P prime lambda. So we fix the T and to investigate the lambda when lambda is greater than 0. And because we know a very special thing is we don't have the L2 known topology to investigate the P prime lambda. So we only can use the tool is the characteristic function. So we focus on first we will introduce some property of the frequency. And next section, we will want to renormalize, like the Professor Hida, how to construction the white noise. And we will put the P prime lambda, the space noise in the R1 minus 1 space. Why we call it R? Because in the German, RAW means the space. So we use the capital R to means the space, like the Hilbert space. So we can introduce the R1 minus 1 as a generalized linear functional, where P prime lambda lives in. And also we want to investigate some P prime lambdas polynomial. But this part is still on work, not yet finished. So I still to do hard work now. And sorry. So the linear functionals of P prime lambda is mean the form like the integral, but actually we analogous to the polynomial summation 10. And we try to use it to investigate. And this F is on the L1 space. First, we have the sorry. First, we have the theory. The theory is if x and y are independent, then the kernel function at f and g, the product will be 0 almost everywhere. So it's just briefly proof. If we can separate the characteristic function, so we can know the proof can be complete. But we know the from 0 to infinity is a little hard to do the scale. So we separate it to 4 parts to do the proof. And because the A, B, C part is very easy to check, so we just focus on the D part. And we differentiate, so we can get the F and G is equal to 0. And their product also equal to 0. And next, our corollary is if the P1 and P2, and P1, P2 is also independent, then the functional of the P1 and functional of P2 also independent too. But in the future, we want to be a Fn function, but now we still work on it. It may be more difficult to research. And the lemma is a little similar to the theory, but it's a little different. We also use the characteristic function to prove the lemma. And because we can get the contradiction, so we know the proof is complete. And now we come to our generalized linear functional. The linear functional with degree 1 means the f is degrees 1, not f2, f squared or f3. And the linear functional from 0 to 1, because we just we first investigate the region is from 0 to infinity. We restrict it to 0 to 1, and then we extend it. First, we know this L1 node can smaller than the F2 node. So we can use the property to differentiate the characteristic function, and we can know the mean and variance. When we construct the mean and variance, we can try to use the mean and variance to construct the R1 space and R1 1 space and R1 minus 1 space. It's like the Gilfang triple. Yes. And when R1 can have this property, we know the triple is like this. So we have the P prime lambda can live in the R1 minus 1. So we can means the P prime lambda is define our Hilbert space R1 minus 1. So we can establish the triple. And the most difficult in my research is how to renormalize the P prime lambda's polynomial. Because we use the Poisson-Charlier polynomial, and we can check the P1 and P2. So Pn, if we put the n is 1, P1 and P2 will orthogonal to each other, and P3 and P4, all the Poisson-Charlier polynomial will orthogonal to each other. And we use it to try to, like the S transform, to do the orthogonalize. So we can use it to renormalize the P prime lambda's polynomial. And the generating function of the Poisson-Charlier polynomial is like this. But now we not yet to use the characteristic. Maybe in the future we will use the generating function to investigate it. And next theory, we also know some property of P prime lambda and where he lives in. So we can know that there exists a generalized stochastic system. It's not an ordinary function of lambda. And about the C-C characteristic function, which defines a generalized system that has an independence value at every point lambda, the lambda intensity. We can define the linear system. Why it's linear system? Because we call the linear process to linear system because the process is focused on P. So we change the term process to system to become linear system. But actually, you can realize it. We call linear system actually is linear process. And because the CF can be expressed like this. So when F is in the space, the intersection L1 and L2, we can get the two moments term like this, or second moment term like this. So we first restrict the integral from 0 to infinity to 0 to 1. And then after that, we will extend it. So now come to our last proposition. The last proposition, we think all the moments will exist. And the first moment will be like this. And the second moment will also be this term. So maybe in the future, we can try to construction the higher polynomial, a higher degree of the polynomial, Rn minus n, and Rnn. If we can do more higher degree polynomials in Vasquez, we may know a lot of property in the space. But I still work on it. And I give some application, but now I still work on it. So the Poisson process may be written as this term, P T lambda. And we know the T and lambda have the dual pair, but actually lambda only can do the transition from minus infinity to infinity. And T can do the transition from minus T to infinity. And lambda only can do the dilation from 0 to infinity. So from its distribution, we may consider T and lambda would play a similar role, but not quite. For final discussion, we may introduce the two-parameter stochastic process and think of the role played by each parameter together with some hidden property between them. And there are many applications in our theory. So one is concerned with the structure of the P prime lambda that creates the fraction power distribution. It's also called stable process, the alpha stable process. Briefly speaking, the parameter lambda of P prime lambda runs through from 0 to infinity in a homogeneous manner. Hence, the dilation group The dilation group is from the Professor CC, who she do some research in the dilation group in the space, in the noise. It's naturally concerned with the fact direct us to consider fraction power density of lambda. With a note of lambda and the span can be related simply. And we also know because lambda in the Poisson process or Poisson distribution, because lambda is invisible. So we use the jump U to try to know some property of lambda. And the jump U also the lattice type of distribution. So we can state the essential difference between the space noise P prime lambda and the Poisson noise P dot T. Both are generalized random systems having independent value at each point. The difference really comes from the type of the domain through which the parameter runs. So it's all my reference and some of my last talk in Myanmar. And thank you. Thank you always for your attention. Thank you.
Questions from the floor?
Can you explain what are you trying to do? You want to build a kind of analog of the white noise space for Poisson.
Yes.
Is this?
Yes.
And your work is related with some work done by Y.J. Lee, Kondraty, and this, who also were trying to do something similar for infinitely divisible processes.
Yes.
Is it so?
Yes. But I meet a lot difficult, so I still try to use a lot of skill or some basic tools to.
But you emphasize the space interpretation of parameter, while usually in the HIDA approach, for example, the parameter is interpreted as a time. So what space is or can be multidimensional in your case? Space parameter.
Sorry, I never really know your question.
Okay, we can discuss this.
Thank you.
Any other questions? Thank you.